Now, when we talked about evidence of a chemical reaction, mentioned that a change in energy is something that we can use as evidence of a reaction. Something might get colder or something might get warmer. So heat can be involved in chemical reactions. Okay, so we have two different things going on. We have exothermic reactions and endothermic reactions. In an exothermic reaction, the reaction gives off energy. And we can feel that happen. So an exothermic gives off, exo, outside. So an exothermic reaction will give off heat. Okay, whereas an endothermic reaction will take heat in. So endothermic needs heat, needs that energy input into it for it to go. And so for an endothermic reaction, we would feel things getting colder. All right, so again, reactions often generate energy or heat. So exothermic reaction will liberate heat. Endothermic reaction will absorb heat. And so for an exothermic reaction, we can put heat as a product. For an endothermic reaction, we can put heat as a reactant. Okay, and so you can see a couple of examples here. All right, so if I look at the combustion of methane, which is what we're using in our Bunsen burners, all right, where do I have energy written? Is energy written as a reactant or a product? Energy is written as a product. So our reaction is exothermic. Okay, it's giving off heat. All right, what about this one? The electrolysis of water absorbs 286 kilojoules for each mole of liquid water decomposed into its elements. Okay, so absorbs, does that mean that we are taking it in or giving it off? Absorbs means we're taking it in, which means this reaction is endothermic. Okay, so we're going to take our 286 kilojoules. Okay, we have some liquid water. Okay, and we get we get H2. I'm looking at this wrong. And O2. Now, thermochemistry is a little bit unique because it likes to do everything per 1 mole. So if I have no coefficient in front of something, it is an implied 1. So what this is saying is for each 1 mole of liquid water, there's 286 kilojoules. So I need to leave this with 1 mole of water. So I have to do a really, really weird thing here. Okay, this is not a normal thing, but for this type of reaction and this type of reaction only, I'm going to balance this with a 1/2 in front of the oxygen. Now, would a real reaction have half of an oxygen molecule? No, it would not. But for cases of putting this to, for every 1 mole of water, I need 286 kilojoules, I would write it like this. Now, if I were to balance this traditionally, what I would need to do is I would need to do 2 times 286, and I would get 572 kilojoules for a traditionally balanced reaction. Since I have 2 moles of water, I need twice the energy there. Okay, so thermochem is a little bit weird in that sometimes when we are dealing with like a standard number, if we have the teller here is each mole. Okay, so that's how I know that this particular reaction is one where I end up having to balance it with that weird 1/2. This is really unusual. We won't do much with this, but sometimes if you're looking up stuff in tables of data, you will encounter this weird stuff with a 1/2 in front of things, but it's only for this specific situation. Okay. All right, here I have octane, hydrocarbon, and gasoline. All right, we're releasing 8.5 times 10 to the third joules of heat. So is this exothermic or endothermic? It's exothermic. Okay. And I'm going to run out of room to rewrite the whole thing, but to write it for exothermic on my product side, I would do my plus 8.5 times 10 to the third joules, because we are releasing heat. So it's exothermic, so it would go on my product side. So that's our little bit of thermochemistry. We're not doing a whole lot with thermochemistry in this class. Just a little bit so that you understand, how heat is involved a little bit in reactions.